Hello guys, welcome to the EduMoon tutorial series. I am Guru Renuka, instructor for the subject Elements of Electrical Engineering, in short EE. So if you find the subject EE difficult, let us make it simple now, okay? In any discipline of science, in order to understand the subject, first of all, we have to be familiar with the basic definitions and terminologies that we use throughout that subject, right? So to understand and to do well in this EE subject, so let's first learn what are the basic definitions and terminologies. So the first chapter, Introduction to Electrical Energy, deals with basic definitions of this magnetic circuit, reluctance, magnetomotive force, and then magnetic flux. And we are also going to know what hysteresis is, and then Faraday's laws of electromagnetic induction, and then induced EMF. So this chapter is basically about the very basic concepts we use in the subject. Okay, so now let's get started. So first we'll learn what magnetic field is. Magnetic field is a space or field in which a magnetic pole experiences a force. So now see what a magnetic pole is. See, when you consider a bar magnet, we know that a bar magnet has two ends, north and south pole. Here the magnetic effect, the maximum magnetic effect can be seen at this north and south poles, right? So we call these two ends as poles. In the same sense, that is what a magnetic pole is. So around this bar magnet, there is generally a magnetic field, right? Yeah, so the space or field in which a magnetic pole experiences a force is called magnetic field. Magnetic flux. It is the total number of magnetic lines of force produced by a magnetic source. First we will see what magnetic lines of force are. Consider a bar magnet. This is the south pole and this is the north pole. Then around this bar magnet, the magnetic field is represented by imaginary lines, okay? That is what we call magnetic lines of force. These magnetic lines of force emerge out from the north side of the pole and then re-enter the magnet through the south side. That is, they emerge out from the north, come out from the north, move in the surrounding medium, then re-enter the pole through the south side. See, in your earlier chapters in your school, you might have learnt about this. And inside, see, from outside it is north to south, and inside it is from south to north. Okay, these lines are magnetic lines of force. So the total number of magnetic lines of force produced by a magnetic source is magnetic flux, which we denote by phi. Okay, and the unit for magnetic flux is Weber. 1 Weber equals to 10 to the power of 8 lines of force, and then 1 microweber, which is micro is 10 power minus 6, so 1 microweber is 100 lines of force. Magnetic flux density. Here the word density itself makes the term clear. Density is the measurement per some unit, per certain volume or per certain area, right? So here the magnetic flux passing normally per unit area. Normally here indicates perpendicular to the plane of the coil. So we just said B equals to phi by A. That is magnetic flux density B equals to the magnetic flux passing normally per unit area. Flux is Webers, right? And area is meters. So units of B will be Weber per meter square. The SI unit is Weber per meter square or Tesla. In units and dimensions, there's a rule. When you indicate a certain unit with the name of a scientist, when you write it down, the first letter should be in lowercase, Tesla. But when you indicate it with a symbol, the capital, you use the capital one, the uppercase one. For example, see Newton, you write it in the lowercase, but when you denote it with a symbol, you use the uppercase, right? In the same sense, here, SI unit of magnetic flux density is Weber per meter square or Tesla. It is a vector quantity. Vector quantity indicates that it has both magnitude and as well as direction. in terms of magnitude, it is B equals to 5 by A. The point is clear, okay. Now we'll see how in terms of direction. Now consider, let this be the plane of the coil and this be the direction of the flux, right? Then this is B and the plane of the coil is inclined at an angle theta to the flux direction. So this will be A cos theta and this will be A sin theta, right? A cos theta, A sin theta. So according to the definition, now the magnetic flux density is the magnetic flux passing normally per unit area. The normal direction, it is A sin theta. Now B equals to 5 by A sin theta, then B equals to, phi equals to B into A sin theta and its units are Weber. Now say if theta is 0 degrees, then sine 0 is 0, then phi is also 0. If theta is 180 degrees, then sine 180 degrees is also 0, right? And then phi is also 0. But when theta is 90 degrees, that means the plane of the coil is perpendicular to the direction, or it is normal to the direction of the flux. Then sine 90 is 1. Then flux equals to BA sine 90, which is 1. So maximum flux is BA Webers, which is obtained when the plane of the coil is normal to the direction of magnetic flux. Now let us see what magnetic intensity is. Magnetic intensity or magnetizing force or magnetic field strength, they denote the same. The symbol is H, okay. So the magnetic field strength at a point in a magnetic field is the force acting on a unit north pole placed at that point. Okay, now we'll make it simple. So consider a magnetic pole M, okay, in a magnetic field. So the magnetic field strength at a point in a magnetic field is the force acting on a unit north pole placed at that point. Okay. So we'll see how it works. So consider a magnetic pole M and a point P in a magnetic field. So this magnetic pole M is at a distance d units from this point P. So we give the magnetic intensity or magnetizing force H as M by 4 pi mu naught into d square. Its units are Newton per Weber. Now see, now what is this mu naught? M is the magnetic pole. Its units are, okay, that is clear then. And d is the distance d. And what is mu naught? First of all, we'll see what mu is. Mu is the absolute permeability. Absolute permeability of the material. Material in the sense this material. If this material is vacuum or air, we denote it with mu naught. So mu naught is absolute permeability of air or vacuum, and mu is absolute permeability or actual permeability of the material. And then mu r. Mu r is the relative permeability of the material, that is mu by mu naught. So mu r is the absolute permeability of the material by absolute permeability of vacuum or air, and this mu naught is a constant. So mu naught has a value 4 pi into 10 to the power of minus 7 h by m. You have to remember this thing, it's useful in calculations. And so magnetizing force H, we got the formula, its units are, SI units are Newton per Weber, and it's a vector quantity. In the case, in the sense, it has both magnitude and direction. So we got, so we know what H is and we know what B is, right? So now let's establish a relation between B and H. B is directly proportional to H. You have to remember this relation because using this single relation, you are going to derive a lot more formulas and a lot more concepts. This is a simple relation. B is directly proportional to H. But okay, now B equals to mu H. Mu is absolute permeability of the material, and then mu can be written as mu equals to mu R into mu naught. So when we substitute this one here, it is B equals to mu R mu naught H. Okay, so the relation between B and H is B equals to mu H. Now let us see what a magnetic circuit is. See, a magnetic circuit, it is the closed path followed by the magnetic flux. That is a magnetic circuit. So in details, so see, in order to produce magnetic flux, the simplest way is consider a magnetic material and then wound a wire around it. So see, I have considered this magnetic material and then I have wound a wire around it, and say it has taken n turns. Now pass a current. So when we wound a wire of say n turns around a magnetic material and we pass a current I, then magnetic flux is produced. So let n be the number of turns and let I be the current flowing through it. So when the amount of this magnetic flux phi is directly proportional to the product of the number of turns and the current I. So flux is directly proportional to Ni. Now we have considered a coil of n turns wound on an iron core. See, as I've drew in this figure in this way. So when current I is passed through the coil, magnetic flux phi is set up, right? Set up in the core, right? So the flux follows a closed path A, B, C, D, A. So it leaves the north pole, passes around the circuit and reaches the starting point. So the magnetic circuit is a closed path followed by magnetic flux. Flux follows a closed path in this core. So phi is directly proportional to Ni. That is the product of the number of turns and the electric current I passing here. So this product Ni is also called as MMF, which is nothing but magnetomotive force. The proper definition of magnetomotive force, we'll learn this proper definition in within few minutes. Okay, so MMF, its units are ampere turns. In short, AT, ampere turns. Okay, so magnetizing force H is Ni by L, so ampere turns by meter. We'll learn this. We'll learn about this in detail in the next few minutes. Now let us see what magnetomotive force MMF is. Magnetomotive force, it is the magnetic pressure which sets up or tends to set up magnetic flux in a magnetic circuit. In other words, it is the work done in moving a unit magnetic pole once around the magnetic circuit. So if you consider a unit magnetic pole, it is the work done in moving this unit magnetic pole around the circuit once around the circuit, and that is what we call magnetomotive force MMF, which is N into I, the number of turns N into electric current I. So MMF equals to Ni and its units are ampere turns. Now we'll see what reluctance is. If you consider electric circuits, in electric circuits, this resistance, right? Resistance which opposes the flow of current. In the same way, in magnetic circuits, we have reluctance, which we denote by S. So reluctance S is opposition that the magnetic circuit offers to magnetic flux. Okay, so S equals to L by A mu naught mu R. Mu naught mu R is permeability of the material, right? So L equals to A mu. We can simply say that. Now see, the reluctance S is it depends upon the length of the magnetic circuit, then the area of the cross section, and then permeability of the material. Remember these 3 points. So the SI unit is ampere turns per vapor. When we compare it with electric circuits, in electric circuit, resistance R is given as rho into L by A, where rho is resistivity. Here reluctance S is given by 1 by mu into L by A, that is mu naught mu R. Okay, both are similar, they both correspond. So this is reluctance. Now we'll see what permeance is. Permeance is easy. See, it is the reciprocal of reluctance. Reluctance is opposition. Here it is ease. Permeance is the measure of the ease with which magnetic flux can pass through the material. So permeance equals to 1 by reluctance. So that is A mu naught mu R by L. Obviously, so its SI units will be the reverse of reluctance. So the SI unit of permeance is Weber per ampere turns. Now we'll focus on the relations that we have learned throughout this session. First we learned that B equals to phi by A, Weber per meter square. Okay, then we got the relation. First we got B equals to phi by A. Okay, then we got the relation B equals to mu H, from which it is H equals to B by mu. And what B is phi by A, right? And mu is mu naught mu R. Okay, this is one relation. Now, and we also got this one, H equals to Ni by L, right? So from this relation and from this relation, when we equate both, phi by A mu naught mu R equals to Ni by L. From this, phi equals to Ni by L by A mu naught mu R. This Ni is MMF, right? And L by A mu naught mu R is reluctance. So flux equals to MMF by reluctance. Does this sound similar? Right, see here. In Ohm's law of magnetic, okay, this one we can also call as Ohm's law of magnetic circuit. Generally what Ohm's law is? Ohm's law is I equals to E by R, right? Here flux is MMF by reluctance S. So sometimes we also call flux equals to MMF by reluctance as Ohm's law of magnetic circuit. Now let us quickly check the similarities and dissimilarities between magnetic and electric circuits. Once if you're clear with the similarities and dissimilarities, then you're pretty much clear with the concept. Okay, it's a quick revise for the entire session too. Okay, first we'll go with the similarities for magnetic circuit and then for electric circuit. Magnetic circuit, it's closed path for magnetic flux, and for electric circuit it is closed path for electric current. Here it is flux equals to MMF by reluctance. Here it is current I is EMF by resistance. MMF, we denote the units are ampere turns, and for EMF the units are volts. Reluctance S is L by A mu naught mu R, that is 1 by mu into L by A. Here our resistance R is rho into L by A, resistivity into L by A. And here magnetic flux B is magnetic flux density B equals to phi by A. Current density J equals to I by A, current by area, cross section area. Units are here Weber per meter square, here it is ampere per meter square. MMF drop is phi into S. Here voltage drop is I into R. And then H, magnetizing force H is Ni by L. Here E equals to V by D. And permeance. Here it is permeance, here it is conductance. Here it is permeability, here it is conductivity. Now let us see what the dissimilarities are. Actually flux does not flow, but current flows in an electric circuit. There is no magnetic insulator, but there are a number of electric insulators. For example, you can even set up a magnetic flux in air, but whereas air offers resistance for electric current. And mu R is not constant. It varies with B, with the value of B, but whereas rho, it varies very slightly with temperature. So practically R is constant. R equals to rho into L by A, right? When it varies very slightly, R is almost practically constant. And see clearly, for creating flux you require energy, but for maintaining flux you don't need energy. And here energy is expended as long as the current flows, and this expended energy is dissipated in the form of heat. And now see, when we connect circuits in a series, consider three different magnetic materials, and when we connect them in a series, then the total resistance is the sum of the total reluctance is the sum of the individual reluctance. S is S1 plus S2 plus S3. But when we connect them in parallel, we add the magnetic flux. Phi equals to phi 1 plus phi 2. See, in a magnetic circuit, in case if there are air gaps, then what to do? How to solve the problems if there are any air gaps? We find the reluctance for this air gap, that is Lg by A into mu naught. See, if it is a reluctance for some material, it is S equals to L by A mu, right? But for air or vacuum, mu is mu naught. So length of air gap by A into mu naught. And the leakage flux. Leakage flux is the total flux minus the flux in this air gap. That is what we call leakage flux. And this leakage coefficient, which we denote by lambda, is phi I by phi g. The total flux by the flux in this air gap. So guys, in this session we learned the basic definitions that we use throughout the subject, and then we also compared between magnetic and electric circuit. So we are done with the first part of the first chapter. So that's it for today's session, and we'll look at the remaining parts in the next session. Thank you guys.